Hello everyone. So Pragvi has come up with a new one-shot series. And in this one-shot series, we'll cover one chapter in a single video. We'll try to cover all concepts, all related numericals and derivations. And we are pretty sure if you watch this one-shot series, you will definitely score above 90% marks in your board exams. So without any further delay, let's begin the session. So in this video, I'm going to cover these topics. So charges and its property, Coulomb's law, electric field, electric dipole, electric field lines, electric flux, and Gauss law and its application. Right. So let's start with the charges. So what is charge? So it is the intrinsic property of the matter, and due to this intrinsic property, one matter can interact with another matter electrically. And what do I mean by electrically? They can exert electric force on one another. So if we have positive charges, say two positive charges, like charges always repel. So they will repel. And if we have two opposite charges, positive and negative, they will attract. So that you have to remember. Now let us see some important properties of charges. First, a very important property which has been asked multiple time in board exam is quantization of charge. So what do I mean by quantization? If there is a body, the charge on this body must be an integral multiple of electronic charge. And what is electronic charge? So charge on one electron is minus 1.6 into 10 raised to power minus 19 coulomb, where coulomb is the unit of charge. So if I say a body is having 2 by 3 E, that charge is not possible on a body. It can't be a fraction. So it must be an integral multiple of E. If I say 1000 E, that is possible. Minus 1000 E, that is also possible. So do remember this. Next property is the conservation of charge. So if I have a system, and in that system, if we have, say, some charge Q, then the charge of that system will not change. It will remain conserved. For example, let us say there is a system and it has three bodies, A, B, and C. And say body A has a charge of 1 coulomb, body B has a charge of 2 coulomb, body C has a charge of 5 coulomb. Now if I add up all these charges, it comes out to be 1 plus 5 plus 2, so that comes out to be 8 coulomb. And say after some time the charge on A becomes, say, minus 1 coulomb, and charge on C becomes 7 coulomb, and charge on B remains same, right? 2 coulomb. Can you see? 7 plus 2 minus 1, again the charge will remain same. So if there are multiple, say, particles in a system, so they can interact with one another, they can transfer charge, charge can transfer from one body to another, but overall charge will remain conserved. So do remember this. Next, electric charge is additive, and the total charge is algebraic sum of the individual charges. So if there is a body, if you give 2E and you will give minus 3E, then the total charge will be 2E minus 3E, which is minus E. So that you should remember. An electric charge does not change if a particle is moving or is at rest. It does not depend upon the state of the particle, right? So electric charge is invariant as it does not depend upon the motion of the charged body or the observer. So next topic is Coulomb's law. So according to Coulomb's law, if we have two charged particles, say Q1 and Q2, I'm taking two positively charged particles, and they are kept at a distance r apart. So they will exert force on one another, and the magnitude of that force will be given by this formula, which is Q1 Q2 upon 4 pi epsilon naught r square, where epsilon naught is the permittivity of vacuum, right? Permittivity of free space, and epsilon naught has a value 8.854 into 10 raised to power minus 12, and the units will be coulomb square meter raised to power minus 2 Newton raised to power minus 1. And permittivity tells us how the particles are interacting, right, with one another. So if we increase the permittivity, then what would happen? The force between the charged particle decreases. If we decrease the permittivity, the force will increase, right? And the value of 1 upon 4 pi epsilon naught, it will be 9 into 10 raised to power 9 Newton meter square upon coulomb square. So the force on particle 1 by the particle 2 will be repulsive, and it will be along the line joining the two charges. So this is the force on first charge due to the second charge, and this is the force on the second charge due to the first charge, right? And these two forces will be, you can say it, they act like a action reaction pair, and we can say F12 will be equals to negative of F21, and both will be having the same magnitude, right? So do remember this. Now if we change the medium, so instead of a free space, if we have some other medium, so here we'll define a term known as a dielectric constant of that medium, or relative permittivity. Now what is dielectric constant? So I can say relative permittivity or dielectric constant will be permittivity of the medium divided by the permittivity of free space. Now, usually for permittivity of the medium, we can represent this with the epsilon, and permittivity of free space is with epsilon naught. So permittivity of the medium can be given as epsilon naught times epsilon r. Sometimes we will write epsilon r as k. So we can also write this as epsilon naught times k. So do remember, for vacuum, the value of epsilon r or k is 1, and for conductor, this value is infinite, right? So it means force will tends to 0. If k becomes infinite, the force will become 0. So do remember this, and do remember the dimension formula of permittivity. It has been asked multiple times. Right. So now let us see the vector form of Coulomb's law. So here we have shown the force on the first charged particle due to the second, and this is the force on the second due to the first. So we can say force on one due to the second will be in which direction? So it is the position. So if I say this vector is position vector of 1 with respect to 2. So R12 can be written as R1 minus R2, right? So we can say F12 is in which direction? So we can say F12 will be parallel to R12. Okay, so here what we have done, so we know the formula, that is Q1 Q2 upon 4 pi epsilon naught R square, and if I multiply and divide by R, we will get Q1 Q2 upon 4 pi epsilon naught R cube times R. Now what is this R? So I can say the force is in which direction? Force F12 is in the direction of R12, right? So we can write this as F12 will be R12. Can you see R12, which is R1 minus R2, and the denominator, the magnitude of this vector, which is cube of that, right? We have a cube of R in the denominator. So this is the vector formula for the force. So do remember this, right? It should be 1, 2, right? Here we have 1, 2. Similarly, we can write down F21, which is Q1 Q2 R12 upon 4 pi epsilon naught R12, not 1, 2. So here it will be 2, 1, right? This will be 2, 1. I hope it is clear to you. So let me give you a general case. Suppose there is a charge Q1 and there is a charge Q2. First, I'll show the position vector. This will be R21, and there is a force of repulsion in this direction, which is F21. So I can say F21 will be Q1 Q2 upon 4 pi epsilon naught R21 vector divided by R21 vector cube, right? So do remember this. Now let us see a question. So two equal balls have equal positive charge Q coulombs are suspended by two insulating strings of equal length. So we have given two charged bodies, identical charged balls, both have charge Q. Now due to the Coulomb repulsion, they will repel each other, and there will be some angle between the two strings. So let us say both the string makes an angle theta with the vertical. Are suspended by two insulating strings of equal length. What would be the effect on the force when the plastic sheet is inserted between the two? If we insert plastic sheet in between, so what would happen due to this plastic sheet? Plastic has a dielectric constant which is greater than 1. So the Coulomb repulsion, which is Q1 Q2 upon 4 pi epsilon naught R square, it will become, that is, the new force will become Q1 Q2 upon 4 pi K epsilon naught R square. So the force of repulsion has decreased by the factor K. So what would be the effect on the force when the plastic sheet is inserted between the two? We can say the force between the two charged particle will decrease by the factor K. So the new force will be original force divided by K. So do remember this, right? Now let us see the next question. Plot a graph showing the variation of Coulomb force F versus 1 by R square, where R is the distance between the two charges of each pair of charges. So let us say we have 1 microcoulomb and 2 microcoulomb. So this is 1 microcoulomb and this is 2 microcoulomb. And if I show the force on charge 2, say 2 microcoulomb due to charge 1 microcoulomb, so I can say F1 will be Q1 Q2 divided by 4 pi epsilon naught times R cube times R vector, right? Where R vector is the position vector of 2 microcoulomb with respect to 1 microcoulomb. Is it clear? Or I can also write it as, so F will be 2 micro square divided by 4 pi epsilon naught R square. So can you see this vector is positive? So I can say this vector is positive, and we have to plot a graph between force and 1 by R square. So if I say y is F and x is 1 by R square, so it is a straight line passing through the origin, right? So y is equals to mx. It is of this form, a straight line passing through the origin. So if I plot, say on the x-axis we have 1 by R square, on the y-axis we have F. So we can say the slope will be positive because it's a, this vector is positive. So this is the slope, right? So this is for 1 microcoulomb and 2 microcoulomb. So that is the graph for 1 microcoulomb and 2 microcoulomb. So if I take a pair 2 microcoulomb and -3, in that case the slope, say let us that force is F2, and it will be 2 microcoulomb times -3 microcoulomb divided by 4 pi epsilon naught R square. Now this vector is negative, right? So I can say it will lie in the fourth quadrant, and its magnitude is greater than the magnitude of the first force. So it means it will make a greater angle with the x-axis. So if this angle is theta 1 and this angle is theta 2, so we can say theta 1 will be less than theta 2, or we can say tan theta 1 is nothing but 2 micro square divided by 4 pi epsilon naught, and tan theta 2 will be minus 6 micro square upon 4 pi epsilon naught. So you can clearly see that tan theta 2 is 3 times tan theta 1, right? So that should be the answer of this question. Right, so now let us see one more question. An infinite number of charges, each of q coulomb, are placed along the x-axis at 1 meter, 3 meter, and 9 meter, and so on. So we have given the x-axis, and there is a charged particle which is placed at 1 meter. Let us say this is x equals to 1 meter, and each charge is having a charge q, and there is another charge which is placed at 3 meter, and there is another charge which is placed at 9 meter. And due to these charges, if all the charges are of the same sign, okay, calculate the electric field at the point x equals to 0. Okay, let me change the question. Calculate the electric force on a charge q naught at the point x equals to 0. So there is a charge q naught at the point x equals to 0 due to these charges if all the charges are of the same sign. Okay, right. Now, since all the charges are of the same sign, this first charge will exert, let us say this is charge number 1, this is 2, this is 3, and so on and so forth, right? So this charge number 1 will exert a repulsive force in the left direction. So this will be, let us say, F1. 2 will exert force in the same direction. This is F2. So all these forces will be in the left direction. So we can simply add the forces. So F1 is 1 by 4 pi epsilon naught q naught square divided by the distance between the two charges, that will be 1 square, right? Similarly, F2 will be q naught, sorry, it's not square, right? q naught divided by 4 pi epsilon naught, and here we have 3 square. And then F3 will be q naught upon 4 pi epsilon naught, 9 square. Okay, so we can simply add them. So we can say q naught upon 4 pi epsilon naught will be common, and we will get 1 plus 3 square plus, or we can say 9 square, and so on and so forth. So what is the ratio first and the second term? It will second term with from the first term, it will be 1 by 9, and if I divide third term by the second term, it is again 1 by 9. So we can say it is a decreasing GP of common ratio 1 by 9. And we know what is the sum of a infinite decreasing GP. It is sum to infinity will be a upon 1 minus r, where a is the first term and r is the common ratio. So it will be q naught upon 4 pi epsilon naught, and first term is 1 and the common ratio is 1 by 9. So this will become q naught divided by 4 pi epsilon naught, 9 by 8. Got it? So it will be 9 by 32, and there is pi epsilon naught in the denominator and q naught in the numerator. So that is the answer of this question. Right, so now let us see a concept of continuous charge distribution. So we have three types of continuous charge distribution. One is a line charge, second is a surface charge, third is the volume charge, right? Now let us see the line linear charge distribution. So if we have a line, and on that line we have a charge uniformly distributed on that length, and if we want to find the force exerted by this line charge on a charged particle placed somewhere close to that line charge, so how we can find the force? So first we will take a small element, and before that we should define a term known as the linear charge density, and the linear charge density is lambda, which is having unit coulomb per meter. So unit of lambda is coulomb per meter. Now if I multiply lambda with a small section of the line charge, it will give us the charge in that section. So in order to find the charge on a small element, and this small element is just like a point charge, and the charge on this element will be lambda times the length of the element. So this is the charge on this element. So now we can apply Coulomb's law between dq and q naught, which is our test charge. So what is the force of repulsion? So df is the force of repulsion. So it will be q naught dq upon 4 pi epsilon naught r square. R is the distance between dq and q naught times a direction, right? So this is basically r cap, unit vector in the direction of the force. Okay, so this is our force, and if we want to find the total force by the line charge, we have to integrate this, right? So if we integrate, q and 4 pi epsilon naught will come out of the integration, and integral lambda dl upon r square times r cap will be in the integral, and will be given some more details in the question. I will be able to calculate this integral, right? So this is the case when we have to find the force by a line charge on a charged particle. Next is a surface charge distribution. Now in case of a sheet, let us say there is a very large sheet, and we want to find the force exerted by this sheet on a charged particle. So we'll take a small area, right? And we have given surface charge density. And now what is surface charge density? Its unit is coulomb per meter square, right? So what is the use of surface charge density? You can multiply surface charge density with a small area and you will get the charge in that area. So the dq will be sigma times ds. So unit of sigma is coulomb per meter square. Now, now we can apply Coulomb force. Since this ds is very small, we can treat it just like a point charge, and then we can apply Coulomb's law. So this is dq, and this is q naught. So the force of repulsion will be df. So df can be written as, so let me write here. So df can be written as q naught times dq divided by 4 pi epsilon naught times r square times r cap. And if we integrate this, so the net force will be given as q naught upon 4 pi epsilon naught integral dq upon r square r cap, and this will be over the entire surface, right? Integral will be over the entire surface. Now the third type of a charge distribution is volume charge distribution. So here we have been given volume charge density, and the unit of volume charge density is rho, is coulomb per meter cube. So if we know rho, we can find the charge on a small volume by multiplying that volume with the volume charge density. So dq will be rho dv. So again, we can consider this small volume as a point charge, and we can find the force on charge q naught by applying Coulomb's law. So df will be q naught times dq divided by 4 pi epsilon naught times r square r cap, and dq is nothing but rho dv, right? So q naught upon 4 pi epsilon naught rho dv upon r square r cap. So the net force on the charge will be q upon 4 pi epsilon naught integral rho dv upon r square r cap. And we have to do this integration over the entire volume. Okay, so the same question has been asked in board exam, so you should know how to find that. Right, so the next concept is electric field intensity, and what is electric field intensity and how to find that. Suppose I have a point charge. I want to find the electric field at a point, say P. So what I'm going to do, I will place a test charge at point P. Let us this test charge is Q naught, and let us say the distance between the test charge and the charge Q is R. Now we'll find the force of repulsion on this test charge, and that force of repulsion will be given by the Coulomb's law. So it will be q naught upon 4 pi epsilon naught r square, right? And if I want to show this in vector form, it will be f vector will be q naught upon 4 pi epsilon naught r square times r cap, right? So this is the force. So electric field is defined as force experienced by the test charge per unit test charge, right? So F by Q naught will be the electric field at point P. So this will be Q naught upon 4 pi epsilon naught R squared times R cap divided by Q naught. So Q naught will get cancelled out. So this will become Q upon 4 pi epsilon naught R square R cap. So you have to remember this formula, that electric field will be given by Q upon 4 pi epsilon naught R square. So it depends only on the distance from the point charge. And here this Q naught has to be very small, otherwise it will change the field produced by the charge Q. So that thing you have to remember, and the unit of electric field will be given by Newton per Coulomb. So the unit will be Newton per Coulomb, and it is a vector quantity. Obviously it is a vector quantity, right? Because it is force upon charge. Okay, right. Now, due to a point charge that we have seen, right, and electric field is inversely proportional to the square of the distance from the point charge. So if we plot the graph of electric field and the distance, it will be electric field will decrease as the distance increases. So do remember this. And in case of a positive charge, the field will be away from the positive charge. But in case of a negative charge, the field will be towards the negative charge. So if this is positive charge Q, if you want to find the field here, the field at this particular point will be away from the positive charge. But if we have a negative charge, then the field at this point will be towards the negative charge. Clear? So that we have to remember. Okay, now let us find the electric field by a ring at a point on the axis of the ring. So we have given a ring, and this ring has a uniform charge distributed over its length. And let us say this charge is capital Q, and we need to find the electric field at a point P, which is located at a distance x from the center, and the radius of the ring is given as capital R, right? So what we're going to do, so when we have an extended body, we'll take a small element. So I'm taking a small element at the topmost point, and let us this element is having a charge dq. Now due to this element, if I want to find the electric field at point P, so I know electric field will be away from the positive charge. So this is the electric field by this point charge. Now if I take another element on the diametrically opposite end, let us say this is having charge dq, and due to this element the electric field will be away from the positive charge. So this is again dE. So if I resolve these electric field along the axis and normal to the axis, you will find that the normal component will get cancelled out. So this component, if I take this angle as theta, so this will be theta, this angle as theta, so this is again theta, right? So d e sine theta component will get cancelled out, and it is true for all diametrically opposite elements. So we have to consider only those components which are along the axis. So we have to only consider dE cos theta component. So dE cos theta. Now what is dE? So dE will be dq divided by 4 pi epsilon naught times r square, where r will be the hypotenuse, which is root of r square plus x square, right? Now let us find dE cos theta. And cos theta will be, if I consider this right angle triangle, so cos theta will be base upon hypotenuse, so which is x upon root r square plus x square. So it will be dq upon 4 pi epsilon naught. Sorry, here we have square, right? So we have r square plus x square, and then cos theta will be x upon r square plus x square raised to power 1 by 2. So in the denominator we have r square plus x square raised to power 3 by 2. So this will become dq times x upon 4 pi epsilon naught r square plus x square raised to power 3 by 2. Since all diametrically opposite element will have electric field along the axis, we can simply add them. So if we integrate this, we'll get the answer, right? Now in this integral, this x and the denominator all are constants. So we can bring them out of the integration. So this will become x upon 4 pi epsilon naught r square plus x square raised to power 3 by 2 integral dq. And this integral dq is nothing but the total charge. Integral dq means we have to add charge on the entire ring, and that is nothing but capital Q. And sometimes 1 by 4 pi epsilon naught is written as k, and this k is not dielectric constant, so don't get confused, right? So electric field at point P will be given as k capital Q x divided by r square plus x square raised to power 3 by 2, right? So this is the electric field at point P. Now let us sometimes I have seen a question where they will ask you at what value of x the electric field will be maximum. So let us find that. So we know EP is k q x upon x square plus r square raised to power 3 by 2. So here I'm going to use maximum minimum approach. So I will differentiate electric field with respect to x, then I'll equate it to 0, and then I'll find the value of x at which that equation is satisfied. And that will be the value at which the electric field will be maximum. So let us differentiate this. So dEP by dx, kq is constant. So now we have to use the quotient rule. So it will be dx by dx, so it will be 1 times x square plus r square raised to power 3 by 2 minus differentiation of the denominator, which is 3 by 2 times x square plus r square raised to power minus 1. So 1 by 2 times 2x, right, divided by square of the denominator. So x square plus r square raised to power 3. Now for this equation to be 0, this factor has to be 0, right? So if I simplify this, so I can take root x square plus r square common. So root x square plus r square is common. So here we'll get x square plus r square minus 3 by 2 times 2x. So this 2 will get cancelled out. For this to be 0, minus 2x square should be equals to minus r square. So x will be r by root 2 plus minus, right? Got it? So it means electric field, if this is the ring and this is the x-axis, let us say, this is the minus x-axis, electric field first at the center, what is the electric field at the center? X will be 0. X will be 0, so electric field will be 0. It increases. So I'm taking upward direction as the positive and the downward direction as the negative, right? If the electric field is pointing in the positive x direction, I'll take it as positive. If it is pointing in the negative x direction, I'll take it as negative. So here, first it increases and then it decreases, at infinity becomes 0. So this is the point, this is x equals to r by root 2. And again, in on the negative x direction, the field will be in the negative x direction. So I'm taking it downward below the x-axis. It will attain a maximum value and then decreases. So this x is minus r by root 2. So here I have taken electric field, right? I hope it is clear. So this is the graph for electric field versus the distance from the center of the ring. Right, so next concept is if we have multiple sources, multiple charges, and we want to find the electric field at a particular point. So first we'll find the electric field by the individual charges and then we'll take the vector addition of those fields. So E will be the vector addition of all the individual fields, right? So we should remember this, right? So here Qi is the ith charge, R I cap is the position vector of the point P from the ith charge unit vector, right? And r square is the distance. I hope it is clear. So I should write it as ri, right? So that you should remember. Reduce the expression for the electric field E due to a system of two charges Q1 and Q2 with a position vector R1 and R2 at a point R with respect to the common origin. Okay, let us see. So we have given 2-point charges. Let us say this is Q1 and the position vector of Q1 is R1 and there is another charge, let us say Q2, and the position vector of Q2 is R2. And we want to find, let us say, the field at point P, and with respect to the origin, the position vector of point P is R. Right, so first we need to find the electric field by the individual charges. So if I join P and Q1, the electric field by P, charge 1 will be E1 in this direction, and electric field by charge 2 will be in this direction, right? Away from the charge. The vector addition of these two fields will be the resultant field, right? So what is E1? So I can write E1 as Q1 upon 4 pi epsilon naught times, say this vector is, let me call it as 3, right? So this will be R31 and this vector will be R32. Now what is R31? R31 will be R3 minus R1, where R3 is the position vector of point P with respect to the origin. So I'll write it as R vector minus R1, right? So this is R31. Similarly, R32 will be R minus R2. So I can write this as electric field by the first charge will be Q1 upon 4 pi epsilon naught R minus R1 cube of that times R minus R1 vector, right? Similarly, electric field by the second charge will be Q2 upon 4 pi epsilon naught R minus R2 vector divided by R minus R2 vector magnitude and cube of that. So if I add these two electric fields, so the field at P will be Q1 by 4 pi epsilon naught R minus R1 divided by R minus R1 cube plus Q2 upon 4 pi epsilon naught R minus R2 upon R minus R2 cube. So that is the answer of this question. Right. So the next concept is of electric dipole, right? And what are electric dipole? Let us say we have two charges plus Q and minus Q, right? They have same magnitude but opposite sign. And we have placed these charges at a distance, say 2L, right? That is, a 2L is the distance between these two charges. So here, this arrangement is known as an electric dipole, and we'll define a quantity, physical quantity, electric dipole moment, which is a vector from a negative charge towards a positive charge. So if I draw a vector from negative towards the positive, I'll say it is an electric dipole moment, and the magnitude of electric dipole moment will be charge on magnitude of the charge on any of the charges multiplied with the distance between them. So that is the magnitude of electric dipole moment, and its direction is from negative to positive. Dipole moment is a vector quantity and is directed from negative to positive, that I have discussed. And the unit of dipole moment will be coulomb meter, right? So Q is in coulomb and the length is in meters. And the dimension will be ampere, time, and length, right? A raised to power 1, T raised to power 1, and L raised to power 1. Because we know that current is Q by T, right? So Q can be written as I times T, and I can, so dimension of I can be written as A, and dimension of time can be written as T, multiplied with the dimension of length, right? I hope it is clear. Now let us find the electric field produced by the electric dipole moment, by an electric dipole, right? So here I'm going to consider three cases. First case will be along the axis. Now let us see what is the axis of the dipole and what is the equatorial plane. So first case at the axis. So this is negative charge, and here we have a positive charge, and let us take the distance between the two charges as 2L, and we want to find the electric field at a point P which lies on the line joining the two charges. Now this position is known as the axial position for the dipole. So if the and usually in this question the distance of point P will be given from the center of the dipole, and this distance, let us take it as R. Now the to find the electric field at P, the electric field by this positive charge will be, so if the distance of the positive charge from P will be R minus L, and distance of negative charge from P will be R plus L, right? Due to positive charge, the field will be in the right direction. Since positive charge is close to the point P, the field, the electric field will be stronger. So this will be, let us say, E plus Q, and due to a negative charge, the field will not that strong, but it will be in the opposite direction. So this will be E minus Q. Now E plus Q is K. K is 1 by 4 pi epsilon naught times Q divided by R minus L square, and E minus Q will be KQ upon R plus L square. Now what is the vector addition of these two vectors? Simply subtract them, right? So electric field at P will be KQ upon R minus L square minus of KQ upon R plus L square. And usually we'll consider a case when R is very large in comparison to the length of the dipole, right? If R is very large, so we can use some approximation in this calculation. If I take R as common in the denominator, so we'll have k cube by r square as common, right? So I have taken k cube by r square common in the both the terms. So I will get 1 upon 1 minus L by R raised to power 2 minus 1 upon 1 plus L by R raised to power 2. And this can be written as k cube by R square times 1 minus L by R raised to power minus 2 minus 1 plus L by R raised to power minus 2. Okay, so now I'm going to use binomial approximation. So what is binomial approximation? So if we have 1 plus x raised to power n, this can be written as 1 plus nx if x is very small in comparison to 1. So in this equation, 1 minus L by R. L by R is very small in comparison to 1 because L is very small in comparison to R. So we can apply binomial approximation. So I can drop this, I can take this exponent and multiply this exponent with L by R. So this can be written as, so this electric field will nearly equals to k q by R square 1 plus 2L by R minus 1 minus 2L by R. Right? So in this bracket, this 1 will get cancelled out and we'll have 4L by R. So we can say electric field at P will be K Q times 4L divided by R cube. Now 4QL is nothing but twice of the electric dipole moment because electric dipole moment magnitude was 2QL, right? So this can be written as 2 times Kp by R cube. Now what is the direction of this electric field? I can say the electric field direction is in the same direction as the electric dipole moment. So electric dipole moment is in the right direction and electric field is also in the right direction. This is the net electric field at the point P. So we can write this electric field in vector notation as 2k p vector divided by r cube. So you should remember this equation. So this is the electric field at the actual position. Now let us see the next position, that is the equatorial position. So in equatorial position, let us say this is our positive charge and this is our negative charge. And we want to find the electric field at point P. And this P point is at a distance r from the center of the dipole and the length of this dipole is 2L. Okay, so again we'll find the field by the individual charges and then take the vector addition of that. So due to this positive charge, the electric field will be away from the positive charge. So this is the electric field. Let us say this is E plus Q. And due to this negative charge, the field will be towards the negative charge. So it will be E minus Q. By symmetry, we can say both these field will be having the same magnitude. So I can say E plus Q magnitude will be same as E minus Q, and that will be K Q upon square of the distance between the charge and that point. So here hypotenuse is root of L square plus R square. So this will be root of L square plus R square and square of that. Right? So this comes out to be KQ upon L square plus R square. So let us take this angle as theta. So if this angle is theta, I can say this angle is also theta. So now I have two vectors and the angle between these two vectors is 2 theta. And both the vector have the same magnitude. So the electric field at P, its magnitude will be 2 times the electric field of one of the magnitude of one of the vector time cos 2 theta by 2, right? So that is the resultant. So 2 will get cancelled out. So it will be 2 times KQ divided by L square plus R square times cos theta, and cos theta is base upon hypotenuse. So in this right angle triangle, base is L and hypotenuse is root of L square plus R square. So L divided by root of L square plus R square, and this can be written as 2K times 2LQ divided by L square plus R square raised to power 3 by 2. Since we are considering only a case when R is very large in comparison to 2L, so this, in the denominator, L square will be negligible in comparison to R square. So we can write L square. So we can write L square plus R square nearly equals to R square. So this can be written as K times, and 2LQ is nothing but the electric dipole moment divided by R square raised to power 3 by 2 will be nothing but RQ. Now here the electric field will be in the downward direction. Now this electric field is opposite to the electric dipole moment direction. So in vector notation, I can say the electric field at point P will be minus Kp vector upon RQ, right? So that is the electric field at a point on the axis, or you can say at a point on the equatorial plane. Now this is the equatorial plane, right? A plane which is bisecting the line joining the two charges. Right, so the third case is electric field at a general point, right? At a general point. So we have given electric dipole. So this is plus, this is minus Q, this is plus Q. And we want to find the electric field at this particular point P. And let us say this angle is theta, and this is the position vector of point P, right? From the center of the dipole. So electric field, so electric dipole moment is in the right direction. Now what I'm going to do in this case, we will resolve, since electric dipole moment is a vector quantity, we can resolve this vector in two mutually perpendicular direction. So I will take two component of this electric dipole. So this component is P cos theta, and there will be another component which is perpendicular to P cos theta, and this component is P sin theta. Now, if I look at point P, so with respect to P cos theta, P is located at the axial position, and with respect to P sin theta, P is located at the equatorial position. So due to P sin theta, the electric field will be opposite to P sin theta. Let me call it E2. And due to P cos theta, the electric field will be in the direction of the electric dipole moment. So this is E1, let us say. So I can say E1. So we know the formula of electric field by the dipole on the axis, and it will be 2 Kp. So instead of Kp, we'll have 2 Kp cos theta upon R cube, right? Its magnitude will be this. Similarly, for P sin theta, it will be minus. So it will be K P sin theta. So I'm taking the magnitude only, right? Upon R cube. Now the net electric field will be the resultant of these two fields. These two fields, E1 and E2, are perpendicular to each other. So it will be root of E1 square plus E2 square. So this will be, so Kp by R cube will come out, and we will be having 4 cos square theta plus sin square theta. And this can be written as Kp upon R cube root of 4 cos square theta can be written as cos square theta plus 3 cos square theta. So it will be 3 cos square theta plus 1. So that is the electric field at this point P in case of a general case. Okay. And what is the direction? So let us say the net electric field makes an angle theta with the R vector. So tan theta will be E2 by E1, and E2 is Kp sin theta by R cube, and E1 is 2 Kp cos theta by R cube. So it comes out to be tan theta by 2. So that is the, okay, let me call it as alpha, right? So this is tan alpha. So tan alpha will be tan theta by 2. Okay, so do remember this derivation. It can be asked in your board exams. So the next topic is when a dipole is placed in external electric field. So first let us take the case of a uniform electric field. So here we have given a dipole. So this is plus Q and this is minus Q. And can you see on the plus Q, what is the force? So we know that electric field is F upon Q, right? So we can say the force will be Q times E. So the charge plus Q will experience force in the direction of the electric field. So this is the force, right? Similarly, the negatively charged particle will experience force opposite to the field. Now, if you take the vector addition of these two forces, it comes out to be a null vector. So we can say if a dipole is placed in external uniform field, the net force on dipole will be 0. Now, due to these two forces, there can be a rotation produced in the dipole because they can form a couple, right? Because their line of application is not same. So they have different line of application. So this is the line of application of the force on minus q, and this is the line of application on the force on the plus q. So what we can say, due to this, if I take this as the center of this dipole, and let us say, let me redraw the diagram. So let us, this is our dipole. This is plus q and this is minus q. An electric field is in the right direction. It's a uniform electric field. And this angle is theta. So the electric dipole moment makes an angle theta with the electric field. And there is a force acting in the right direction QE, and there is a force QE acting in the left direction. And we want to find the torque. You can find torque about any point, you will get the same answer. So I'm finding the torque about the center, right? So this length is L. This length is also L, right? So what is the perpendicular distance of this point O, point O from the line of application of QE? So that will be L sine theta, right? Similarly, the point of application, so the line of application of QE on plus Q, its perpendicular distance from O will be again L sine theta. Now, due to QE, due to this force will try to rotate this dipole in the clockwise direction, and this force will try to rotate it again in the clockwise direction. So we can simply add the two torques. So we can say QE L sine theta plus QEL sine theta should be equals to, since it's a rotation about a fixed axis, we know that the net torque by the external forces will be equals to I times alpha, where I is the moment of inertia of the system about the axis of a rotation. So what is the moment of inertia of this system? Let us say both these charges have a mass m. So when we have mass m, then the distance of this mass m from the axis of rotation is L. So we can say the moment of inertia of the system will be 2 times ml square. So 2 times ml square times alpha. So this comes out to be 2 QE L sine theta. Okay, right. So basically we need to only need to find the torque, right? So let me just find the torque first. So torque will be, what is this? 2Q times L. This is nothing but the electric dipole moment. So we can say it will be P E sine theta. If I want to write this in vector notation, so I can say it will be P cross E, right? So do remember this derivation. So which is, so when we place a electric dipole in an electric field, it will experience a torque, and this torque will try to align this dipole in the direction of the external electric field, right? And the angle between the electric dipole moment and the field is theta. Okay, right. Now there is one more question based on the same concept. Is, suppose if there is an electric dipole which is aligned with the electric field, there is an electric dipole which is aligned with the electric field. If we tilt this dipole slightly, let us say now we have rotated this dipole by an angle theta, and this theta is very small. And the question is, what is the time period of small oscillation? So this is a question of angular SHM. So let us say, so we know that the torque will be PE sine theta. And since we have rotated this dipole in the anti-clockwise direction, there will be a torque in the clockwise direction, because torque is in the direction of P cross E, and P is in this direction, E is in this direction. So P cross E, it is into the plane, and theta, so angular displacement is out of the plane. So they are in opposite direction. If theta is very small, sine theta can be written as nearly theta. So this can be written as tau equals to minus PE theta. So why I have written minus? Because the torque and the theta both are in the opposite direction. And by rotation about fixed axis concept, we can say torque can be written as I alpha. So I alpha, so it will be minus PE theta. So from here we can say alpha is the angular acceleration, will be minus PE by I times theta. Now this equation is an equation of angular SHM. So according to angular SHM, alpha is directly proportional to the angular displacement. So it is alpha is equals to minus omega square theta. So the constant of proportionality is omega square. Now if I compare this equation with this equation, I can say omega square is PE by I, and omega will be square root of PE by I. So and we know that the time period of small oscillation will be 2 pi by omega. So this comes out to be 2 pi times root of I upon PE. If we have this kind of arrangement, let us say there are two masses and its charge is plus q and its charge is minus q, then the moment of inertia, if this length is L, this length is L, so the moment of inertia will be 2 times ml square, right? So we can substitute the value of I in this formula and we can find the time period. I hope this concept is clear to you, right? Now let us see a very important concept, that which it is the energy of a dipole in external field. So let us say we have a electric dipole and it makes an angle theta with the electric field. So we'll define the potential energy of this electric dipole in the electric field as minus P dot E. So it is minus PE cos theta, right? So when do we have maximum potential energy? So U will be maximum when cos theta is minus 1, right? What do we mean by this? When electric field and dipole are anti-parallel to each other, when the angle between them is pi, then cos pi we know that it is minus 1, right? And the potential energy will be minimum. And what is the potential energy will be maximum. And what is the maximum value of potential energy? It will be PE. And this is also known as a unstable equilibrium configuration, right? Now if and what is the minimum potential energy? So it will be when the cos theta is equals to plus 1. So U minimum will be minus P. And when do we have cos theta is 1? When theta is 0. So when both electric dipole moment and electric field are in the same direction. So here theta is 0 degree. So this is known as stable equilibrium configuration, right? And when do we have potential energy 0? So we have assumed potential energy to be 0 when both are perpendicular to each other. So when electric dipole moment and electric field are perpendicular, then we can say U will be 0. So do remember this concept, and usually there is a question from this unstable equilibrium and stable equilibrium configurations. And what happens if we have an electric dipole in a non-uniform electric field? So let us see. In non-uniform electric field, let us say this is minus q and this is plus q. In that case, let us there is a force QE1 in this direction, and let us say there is some force QE2 in this direction. In this case, there will be some net force acting on the dipole because electric field is non-uniform. So F net will not be equals to a null vector, but there will be a torque, right? And torque will be again non-zero. So in this case, torque will be non-zero and the force is also non-zero. But if we have a uniform electric field, the torque will be non-zero, can be non-zero, and force will always be 0. So do remember this. Right, so the next topic is electric field lines. Okay, right. So if we have a positive charge, then the electric field lines can be drawn in the radially outward direction. So this is the direction of electric field, right? In the radially outward direction. Similarly, for a negatively charged particle, we can show the direction which is radially inward. So like this, we can show the electric field line for positive and the negative charge. Now, if we have given, let us say this is a electric field line direction given to you. If I draw a tangent at this particular point, so this tangent will give us the direction of electric field at this particular point. For example, at this particular point, if I draw a tangent, so it will be in this direction. And the third most important property of electric field line is no two electric field line will intersect each other. Why they cannot intersect? Because if they intersect at this particular point, there will be two tangents, right? If there are two tangents, I can say there are two directions, and it is not possible for electric field to have two direction at a particular point. And suppose if we have a conductor, if there is a conductor, if I place a charge, say positive charge, and we in that case the electric field line will always be normal to the conducting surface, right? So we'll show it like this. So like this, we can show the electric field line due to a positive charge and a conducting surface nearby. So, and it always enters normally, right? Do remember this. And there is one more important concept. If I consider, say, point A and point B. So can you see at point A, the electric field line are quite close to each other, but at point B, the electric field line are quite far apart. So this density of electric field line tells us the strength of the electric field. Closer the lines, stronger the field, farther the lines, the weaker the field. So do remember this. And the number of electric field line originating from a charge tells us the magnitude of the charge. For example, if I have 1 coulomb charge, and if I'm showing 4 electric field line, for 2 coulomb charge, I will show 8 lines, right? Got it? So these properties you have to remember. And this is one more important concept. If I have this kind of arrangement where the gap is continuously decreasing, so we can say at this point the electric field is in the right direction. At this point the electric field is also in the right direction because these are the direction but tangent. But if this point is A, this point is B, at A we can say the electric field are quite far apart, electric field lines are quite far apart, but at B the electric field line are quite close to each other. So we can say electric field at B is stronger than the electric field at A, though the direction is same. Both are pointing, the electric field is pointing in the right direction at A and B. In this case, we have given curved field line. Electric field at A point is pointing in this direction, at B point it is pointing in this direction. So here the direction is changing. Got it? But the gap between the electric field line is nearly same, so we can say they will be having nearly same magnitude. So at B and A the magnitude will be same, but the direction will be different. Now in this case, if I consider point A, another point B, so at A, let me take A on a line set, right? So at this point the electric field is pointing in this direction, and let me take this point as B. So here the electric field is pointing in this direction. At A and B the direction has changed. Even the separation between the line has also changed. At A, the electric field line are quite close to each other, but at B, the lines are quite far apart. So we can say electric field at B will be weaker as compared to electric field at A. If in this particular arrangement, if we consider point A and point B, at A, the electric field is in the right direction. At B, the electric field is in the right direction. And even the separation between the lines at A and B is same. So we can say magnitude as well as direction both are same. So this is a case of a uniform electric field, right? This is a case of non-uniform electric field. Okay, right. Now, if we have to show electric field line for a system of charges, for example, if we have two positive charge, so this is how the electric field line look. Because if I consider a point somewhere here or anywhere on a line on an equatorial plane, anywhere a point on an equatorial plane, at every point, at this particular point, okay, at this point it will be 0. That is pretty clear. At this point, we know that it will be pointing in this direction. So I can show it like this. At this, it will be like this, right? Clear? So like this, we can show the electric field line in case of a two positively charged particles. Similarly, if we have a dipole, in case of a dipole, the electric field line will be given by this diagram, right? So can you see the electric field will originate from positive and terminate on a negative, and it should be normal, right? It should enter normally. So all these angles should be 90 degree. So do remember this. Now the next concept is electric flux. Now what is electric flux? So qualitatively we can say electric flux is the number of field line which is piercing a particular area. And mathematically we can say electric flux will be given by E dot dA, where dA is a area, right? For example, if this is the area and the direction of a area is given by the normal direction. So if this square has a area dA, then its direction will be normal to this area. So this will be the dA vector. And if at this area, this is the electric field, then I can say the angle between these two is theta, let us say. Then the dot product of these two vector will give us the flux, and flux is represented with phi. So I can say d phi, or small flux linked with this small area, will be E dot dA. So do remember this. It's a scalar quantity because it's a dot product. So it can be written as E dA cos theta, right? And what is the unit? It will be voltmeter or Newton meter square per coulomb, and this is the dimension. Right, so let me take example. So if there is a area, let us say this is A and this is B, and the electric field, which is say 10 Newton per coulomb, it makes an angle of 37 degree with the plane. Now what is the direction of the plane? It will be normal to the area. This is our area vector, right? And the angle between the electric field and the area vector is 53 degree. So the flux linked with this area will be EA cos 53 degree. Electric field is 10, area is A times B, and cos 53 is 3 by 5. So it comes out to be 6 AB volt meter. Got it? So when we have a uniform electric field, in that case, the flux will be given by E dot A, where A is the area of that particular, A is the area and E is the electric field at that area. But if we have a non-uniform electric field, let us say there is an area and electric field is non-uniform on this area. So we'll take a small element. So this is say dA, which is pointing normal to this. And let us say at this area, the electric field is pointing in, say, in this direction. This is electric field. They will find d phi. So d phi is the flux linked with this small area. So it will be E dot dA. And the integral of this will give us the total flux linked with this entire area. Integral E dot dA. Got it? Now let us see some illustration, so you'll be able to understand concept more clearly with these illustrations. So what is the flux due to electric field, which is 3 into 10 raised to 3 I cap, through a square of side 10 centimeter, which is held normal to the electric field, which is held normal to the electric field. So there is a electric field, that is the electric field is pointing in the right direction, which is 3 into 10 raised to 3 I cap. And there is a square area which is held perpendicular to the electric field. So what I can say, the area vector, I can take the area vector in the direction of the electric field. So I'm taking this normal as the area, right? Now what is this area? What is the magnitude of this area vector? So it will be nothing but the area of this square. So that will be 10 times 10 centimeter square. So this will be 100 centimeter square. So in SI unit, this will be 100 times 10 raised to power minus 4 square meter. So that would be 10 raised to power minus 2 square meter. Now we know the area. And the angle between the area vector and electric field is 0 degree. So cos 0 will be 1. So E dot A will be 3 into 10 raised per 3 times area will be 10 raised per minus 2 cos 0. So this will be 30, right? 30 voltmeter. I hope it is clear. Now let us see one more question. Consider a uniform electric field which is 3 into 10 raised per 3 I cap. Calculate the flux of this field through a square surface of area 10 centimeter square when its plane is parallel to the YZ plane. This one we have already discussed, right? When its plane is parallel to the YZ plane. So it is similar to this case, right? This area lie in the YZ plane. The normal to this its plane makes an angle of 60 degree with the x-axis. So if this is the electric field, I'm doing the second part. So electric field is 3 into 10 raised per 3 I cap, and the area makes an angle of 60 degree with the electric field vector. So area will be 10 square centimeter. So it will be E A cos theta. So E is 3 into 10 raised per 3. A is 10 into 10 raised per minus 4 times 10 into 10 raised per minus 4 times cos 60 degree. So this will become what? 3 into 10 raised per 3 into 10 raised per minus 3. Cos 60 will be 1 by 2. So 1.5 will be the answer. So this will be in the voltmeter. So that is the flux. I hope it is clear to you. Okay, right. So the next concept is Gauss law. And with this law, we can find flux linked with a closed surface, or we can also find the electric field by symmetrical current elements. Now let us see what is this law. So according to this law, if we have a closed surface, let me take a closed surface. Let us say this is the closed surface. And within this closed surface, there are some charges. Let us say Q1, Q2, Q3. And there are some charges which are placed outside. Say Q5, Q4, right? These are placed outside. So according to this law, if we find the flux through this entire surface, which is closed integral E dot dA, it comes out to be equals to the net charge enclosed by this closed surface divided by epsilon naught. Now, what is the enclosed charge in this case? It will be sum of Q1, Q2, and Q3. So Q enclosed will be Q1, Q2, and Q3. And we have to add charges algebraically, right? If we have a negative charge, we have to take it as negative only. So let us say some important points about Gauss law. First, it does not depends upon the shape of the Gaussian surface. This is known as a Gaussian surface. And the flux does not depend upon the shape of the Gaussian surface. For example, let me take two cases. So let's say this is the first Gaussian surface and there is a charge Q. And let us say this is the another Gaussian surface and there is a charge Q, right? In both the surfaces, the flux will be same. It will be Q by epsilon naught, right? And flux through a Gaussian surface depends only on the charges present inside this. Yes, because the right hand side is Q enclosed by epsilon naught. And flux through Gaussian surface is independent of the position of the charges. Even if you move this, if there is a Gaussian surface, if I move a charge from this position to another position, the charge enclosed will not change. So it does not depend upon the motion of the charges within the surface. Electric field intensity at the Gaussian surface is due to all the charges present. So in this particular question, so in this particular illustration, if I take a point A, at point A, the electric field will be vector addition of electric field by all the charges. So this will be E4, this will be E5, this will be E2, and this will be E1, and similarly this will be, sorry, this is E3, right? And this will be E5. So at A, the field will be vector addition of all the individual fields. So this you have to remember. So in a closed surface, incoming flux is taken as negative. So if I have a, say, a positive charge, and let us say this is the Gaussian surface. So in this case, the electric field line, if I show electric field lines, they are radially outward, right? So in this case, the electric field line are piercing in the outward direction. So I will take, so the flux will be positive in this case. But if we take a negatively charged particle, and if this is the Gaussian surface, in this case, the electric field lines will be inward. If electric field lines are inward, we can say the flux will be negative, because in case of a closed surface, we'll take area vector is always outward normal. So by convention, we'll take it outward normal. So if I consider any area, so at this particular point, the area vector will be outward normal, and electric field is in this direction. So the angle between the area vector and the electric field is obtuse. So it comes out to be negative. So in Gaussian surface, if flux is zero, we can say the charge enclosed will be zero, right? It does not implies that E will be zero. If phi is zero, it means integral E dot dA is zero, right? It does not tells us that E is zero, right? E can be zero, can be non-zero. For example, if there is a Gaussian surface and there is a charge plus Q and there is a charge minus Q. If I consider a point, at this particular point, there is an electric field in this direction, there is an electric field in this direction. So the resultant of these two fields will be somewhere in this direction, right? So at this point, the field is non-zero at different points, but the flux will be zero because Q minus Q is zero, because Q enclosed is zero, right? So, but if electric field is zero, we can say the flux will be zero, right? If E is zero, integral E dot dA will be zero. So flux will be zero. For example, this case, there is no charge enclosed. So at every point, the field is zero. If field is zero, flux is zero, right? I hope it is clear to you. So do remember these points, and you can write down these points in your board exams if there is a question of Gauss law. Now let us see some of the illustration which will further strengthen your concept about Gauss law. Figure shows 3 point charges plus 2q minus q plus 3q, and 2 charges plus 2q and minus q are enclosed within the surfaces. What is the electric flux due to this configuration through the surfaces? Very easy question. So we have to simply add up the charges which are enclosed. So q enclosed will be 2q minus q, that will be q. So flux will be q enclosed by epsilon naught. So it will be q by epsilon naught. Right, now let us see one more case. A hollow cylindrical box of length 1 meter and area 25 square centimeter is placed in a 3-dimensional coordinate system as shown in the figure. The electric field in the region is given by 50x. So electric field is not uniform, it is variable, 50x. Where E is in Newton per coulomb and x is in meter, find the net flux through the cylinder. Now in this case, electric field is non-uniform. So what we're going to do, so we'll consider different areas, right? So can you see there are 2 flat surfaces and 1 curved surface. An electric field is pointing in the x direction. So if I consider any small area on the curved surface, that is, this is the small area on the curved surface, and we know that I have to take the outward normal as the direction of the area vector. So this dA will always be perpendicular to the electric field. If you take any area on the curved surface, the area vector will always be perpendicular to the electric field. So if that is the case, the flux linked with the area, curved surface area, will be zero. So we can say flux through curved surface is zero because electric field is perpendicular to the area vector, right? Now we are left with only 2 surfaces, left flat surface and the right flat surface. So if I consider this left one, so we know that the outward normal will be in the negative x direction. So this is, let us say, A1, which is pointing in the negative x direction. An electric field will be in the positive x direction. And at this area, the x coordinate is same. And what is the value of x coordinate? It is 1 meter. So we can say electric field. So if I consider left area, area vector, its magnitude will be what? So we have it has a cross sectional area of 25 square centimeter. So this will be 25 square centimeter. And electric field, its magnitude will be what? It will be 50 times 1. So 50 Newton per Coulomb. Right? So we know the electric field, we know the angle between the area vector and the electric field. So the angle is 180 degree. So E dot A1 will be E A1 cos 180. So that comes out to be minus 50 times 25 into 10 raised to power minus 4. So I have converted centimeter square into meter square. So I have multiplied this with 10 raised to power minus 4. So this comes out to be 125 into 10 raised to power minus 3, or I can say 0.125 volt meter. So that will be the flux, electric flux linked with the left phase. Similarly, we can find the flux through the right phase. So at the right phase, the area vector will be in the positive x direction because the area is always outward normal in case of a closed body, a closed surface. So this is A2, let us say, and electric field is also pointing in the x direction. So both are in the same direction. So cos theta will be 0 degrees. So cos 0 is 1. So the flux through the right phase will be E A2, right? E is 50 times, and the length of this is 1 meter, right? So we can say the coordinate, x coordinate at the right face is 2 meters. So it will be x 50 times 2 times the area, that is 25 into 10 raised to power minus 4. So this comes out to be what? It will be 25 into 10 raised to power minus 2. So it will be 0.25 volt meter. Now this is the flux through the right phase. So what is the net flux? So net flux will be flux through the curved surface, flux through the left surface, flux through the right surface. So curved surface is 0, left surface it is minus. Sorry, there is a negative sign, right? So it is minus. So minus 0.125, and through the right surface it is plus 0.25. So answer will be 0.125 voltmeter. So that is the net flux linked with this closed surface. Now, since we know the net flux, we need to find the charge enclosed by the cylinder. So charge enclosed by Gauss law will be net flux times the epsilon naught. So epsilon naught times 0.125, and we know the value of epsilon naught, it is 8.854 into 10 raised to the minus 12. Multiply that with 0.125, you will get the answer. Right. Now let us see one more case. So here, state Gauss's law in electrostatics. So we have already done this portion, right? What is the Gauss law, right? A cube with a side A is kept in an electric field given by Cxi cap. So electric field is in this direction and it is given as Cxi cap, where C is a positive dimension constant. Find out the electric flux through the cube. Again, it is similar question. If I consider lateral surface of the cube, for example, this one, this area, right? All the lateral surfaces, the electric field will be perpendicular to the area vectors. For the top surface, area vector is in the upward direction, electric field is in the right direction. For the front surface, the electric field is in the right direction, area vector is normal to that. Or you can say it will be in the z direction, right? Area vector in the z direction. So we can say flux linked with curved or not curved surface, lateral surface will be 0. So we are left with only left surface and the right surface. Now this is the left surface, and area vector is always outward normal, so it will be in the left direction. Let us, this is A1, and electric field is in the positive x direction. So that will be, and the value of x on the left surface is A, so this will be CA. So electric field is CA, and the angle is 180. So flux through left face will be minus A1 and A, and it's a cube of side A, so it will be A square. So A square times CA, so which is minus CA cube. Similarly, for the right face, area vector will be outward normal, so this is the area vector, and electric field is also in the right direction. And at the right face, what is the value of x? It is 2A. So it will be 2, so C times 2A, right? So C times 2A is the electric field. So we can say the flux through right face will be C 2a times a2, which is a square. So this will be 2a cube c, right? So what is the net flux? So net flux will be sum of all the individual flux. So through the lateral surface it is 0, and through the left it is minus ca cube. Through the right it is plus 2 ca cube. So it comes out to be ca cube. So that is the answer of part A, where we have to calculate the electric flux. Now the second part is the charge enclosed, and we know that by Gauss's law the flux will be given as q enclosed by epsilon naught. So q enclosed will be epsilon naught times ca cube. So that is the answer of second part. Now let us see the example of a cube Gaussian surface, and if we place a charge at different locations inside the cube, then what is the flux through the cube? So let me take a very basic case. There is a cube and charge is placed at the center of the cube. So these are the 6 faces, and we have placed the charge at the center of the cube. So we can so by Gauss's law, if I consider this cube as my Gaussian surface, then in that case the flux will be q by epsilon naught, right, through this cube, right? If you want to find what is the flux linked with one of the face, so by symmetry we can say all phases are symmetrically aligned with respect to the charge. So by symmetry, flux through any phase is same, and it will be total flux divided by 6. So it will be q upon 6 epsilon naught. If I give you another question, let us say there is a square face and the side is A, and if we place a charge at a distance a by 2 from the center of this face, right, and say this is the charge q. Now if the question is what is the flux linked with this area due to this charge, so what you can say, we can draw a hypothetical cube, right? So this is the hypothetical cube, and now we have a same situation like this, where a charge q is placed at the center of a cube. So the flux linked with one phase will be q upon 6 epsilon naught. So do remember this concept. Now if we have a charge placed at one of the corner, now this is our cube and we have placed a charge q at the corner. Now what is the flux linked? So how much flux is crossing through this cube? Since this charge q lie in the top face, left face and the back face, right? So the flux linked with those faces will be 0, right? If I consider this is the back face, this is the left face, and there is a charge here, the electric field lines due to this charge will be parallel to the face. Similarly, electric field line linked with the back face will be parallel to the face, so there will be no flux linked with these two faces. Even if I take the top face, the electric field lines are parallel to the surface. So we can say there will be no flux linked with the top face. So we can say flux through top is equals to flux through left is equals to flux through back, and all of these will be 0. So if we want to find how much flux is piercing through the cube, so we can say there will be a flux through other faces, front, right, and the bottom face. And how much is that flux? So what we can do, we can assume that this charge q is placed at the center of a cube of side 2a. So if this is A, so we'll draw a hypothetical big cube, and this q charge is placed at the center of that big cube. So due to that, we can say this charge q is symmetrically aligned. So the flux linked with one of the cube. So how many cubes are there? There are 8 cubes, right? So there are 8 cubes. So 1, 2, 3, 4, and 4 below that. So there are 8 cubes, and all cubes are symmetrically aligned with this particular charge. So the flux linked with every cube will be same. So if the total flux is q by epsilon naught, then the flux linked with one of the cube will be q by 8 epsilon naught, right? So in this case, flux will be q by 8 epsilon naught. Again, the front, if I consider this particular cube, the front face, the right face, and the bottom face are symmetrically aligned with respect to the charge. So we can say they will share equal flux. So this is the flux through one cube. So flux linked with, say, right face will be same as the bottom face, will be same as the bottom front face, right? And this will be equal to q upon 24 epsilon naught, 1/3 of this, right? Okay, right. So now let us see one more example. If a charge is placed at the center of one of the face, so let us say this is our cube. So we have given this cube, and the charge is placed at the center of the right face. Okay. So what we're going to do? So we will draw a hypothetical cube to the right of the charge, such that this charge cube will be at the center of this cuboid, right? So now we have a cube of side A. We have drawn a hypothetical cube of side A. Now we have a cuboid of dimension A, 2A times A times A, right? Now this cube is placed at the center. So by symmetry, what I can say, the flux linked with the left cube will be same as the flux linked with the right cube. So in this case, so the total flux linked with this cuboid is q by epsilon naught. So half of that will be q by 2 epsilon naught. So in this case, the flux linked with one cube will be q by 2 epsilon naught. So you have to remember this case. Let me again revise like whatever we have studied here. So we have a cube. If this cube is placed at one of the corner, in this case, the flux linked with the cube will be q upon 8 epsilon naught, and flux linked with one of the face will be q upon 24 epsilon naught. And if the charged particle is placed at the center of the face, in this case it will be q by 2 epsilon naught with the entire cube, right? Now let us see how we can find the electric field by a symmetrical charge distribution. Let us take a case of an infinite long straight wire. So we have given a long straight wire which is having uniform charge distributed along the length, and here we have given lambda. So lambda is linear mass density, not mass density, sorry, charge density, linear charge density, and its unit is coulomb per meter. So if I want to find the if I want to find the charge on a particular length of this infinite wire, then that charge will be linear charge density times the length of that uh, element, right? So we want to find the electric field at some particular perpendicular distance. Let us say I want to find the field at a distance r from the infinite line charge. So what we're going to do, we'll consider a hypothetical Gaussian surface, a cylindrical Gaussian surface, right? And the axis of this Gaussian surface is aligned with the line charge. So this is I'm considering. Let us say the length of our Gaussian surface is L, and the radius of the Gaussian surface is R. Now this Gaussian surface has two flat surfaces and one curved surface, and by symmetry we can say the electric field lines will be perpendicular to the line charge at every point. So we can say at the top face the electric field line will be aligned with the area, right? So it means if electric field is parallel to the area, there will be no flux linked with that area, because area vector is normally outward, right? So this is the area vector. Electric field is parallel to the area, so there will be no flux linked with the top surface. Similarly, we can say there will be no flux linked with the bottom surface, because area vector will be in the downward direction. In a closed surface, we always take a outward normal as the area vector. So this area is perpendicular to the field, because field is parallel to the area. So we're left with only curved surface. And by symmetry, we can say every point on the curved surface is at a distance r from the, at a perpendicular distance r from the line charge. So if we apply Gauss's law, so according to Gauss's law, closed integral E dot dA, it can be written as integral E dot dA for top surface plus integral, not closed, right? Open integral. Because now we are considering open surfaces one by one. E dot dA bottom plus integral E dot dA curved. So these two will be zero because electric field is perpendicular to the area. So we are left with the open integral E dot dA for the curved surface. Now, and by symmetry, at every element, if I take a small area element on the curved surface, at this element, the electric field will be parallel to the area vector. So this is electric field, this is dA, right? At every point, right? If you take any area on this curved surface, the electric field will be parallel to the area vector. If that is the case, and by symmetry, we can say every area will be at a same distance from the line charge. Perpendicular distance will remain r only. So E will be having the same magnitude at every point. So this can be written as integral E dA cos 0. And E can also be, we can bring E out of the integral because E has a constant magnitude on this curved surface. So E will come out, so integral dA. And integral dA is nothing but the total surface area of the curved surface. So this will be, it's a curved surface, so 2 pi r L, area of a curved surface of a cylinder. And by Gauss's law, integral E dot dA can be written as Q enclosed by epsilon naught. So how much length of the infinite line charge is contained in this cylinder? It will be the L length, right? So what is that charge? It will be lambda times the length of the conductor divided by, lambda times the length of the line charge divided by epsilon naught. And the left hand side is E times 2 pi RL. So this will be lambda L by epsilon naught. So L will get cancelled out. So electric field will be lambda upon 2 pi epsilon naught R. And this can also be written as 2 times K lambda by R. So you should remember this. This derivation can be asked in board exams. Next, electric field due to uniformly charged thin spherical shell of uniform surface charge density sigma and radius r at a point distance r from the center of the shell. Okay, right. So we have given a shell, and this shell has a uniform surface charge density sigma, and this shell has a radius capital R. Sigma is the surface charge density, and we need to find the electric field at a distance r. Now, in this case, we can have two different cases. One case would be when the point at which we want to find the field lies inside the shell, and the second case when the point lies outside the shell. So I'm considering first case when it is lying inside the shell. So if I consider a spherical Gaussian surface, right? Because we have a spherical body. So we'll take a spherical Gaussian surface. Due to symmetry, or you can say in this case, if you take this Gaussian surface, let me call it 1. In this case, since there is no charge enclosed, so flux will be 0, right? And by symmetry, if suppose E is 0 in this case, but why that is 0, let us see. Let us say at this particular point, the electric field is in this direction, which makes some angle theta with the radial direction, right? If I take any other point, let us say this point, here again, the electric, by symmetry, we can say if electric field will be somewhere here, which is making an angle theta with the radial direction. So if I apply integral E dot dA, so this can be written as E dA cos theta. So theta will be same for at every point because we have a symmetry here. Now, again, by symmetry, we can say this E must be having a constant magnitude. So E can come out. So we have integral dA cos theta. Even cos theta is also constant for every point on the surface. E cos theta integral dA. And this is equals to 0 because the charge enclosed is 0. So from here we can clearly see that integral dA is non-zero, cos theta we can say it is non-zero, so E will be 0. Is it clear? So that's why the electric field at any point inside the shell will be 0. Now if you want to find the field outside, so we'll consider a separate Gaussian surface. This is our second Gaussian surface and the radius, let us take it as small r, and small r is greater than capital R, right? So if you can calculate the charge enclosed, then the entire shell is inside this Gaussian surface. So we can say Q enclosed will be sigma times the surface area, that will be 4 pi capital R square. If I divide this by epsilon naught, so this is the flux. And by symmetry, we can say at every point, the electric field will be radially outward. So if I take any area, the electric field and the area vector, they will be parallel to each other. So I can show the electric field lines. So it will be something like this, right? Radially outward. So electric field will be normal to any small area of the Gaussian surface. So flux can be written as integral E dot dA can be written as EDA, integral EDA, because cos 0 is 1. And since E is having, by symmetry, E must be having a constant magnitude on the Gaussian surface. So we can take E out. So this will become integral dA, E times integral dA, and this can be written as E times 4 pi small r square. Got it? So by Gauss law, we can say E times 4 pi small r square will be equals to sigma 4 pi capital R square by epsilon naught. So E 4 pi r square will be sigma by epsilon naught 4 pi capital R square. So this 4 pi will get cancelled out. So E comes out to be sigma by epsilon naught R square upon small r square. So that will be the electric field outside the sphere, right? And sometimes you have to plot the graph. So so let us plot the graph of electric field with the distance from the center. So up to capital R, the field is 0, and then it increases, and then it will decrease as R increases, right? Because it is inversely proportional to the square of the distance from the center. Okay, now let us see the next case. Electric field due to a thin non-conducting infinite sheet of charge with a uniform surface charge density. Basically, we have given an infinite sheet. Let us say the surface charge density is sigma. And we want to find what is the electric field. And by symmetry, we can say the electric field will be normal to the surface and it will be away from the positive charge. So let me show it in one dimension. So this is our, let us say this is our surface charge. This is our infinite line surface charge, which is having charge, positive charge, so surface charge density sigma. So here basically I'm considering a Gaussian surface, a cylindrical Gaussian surface like this. Half of the cylinder is to the right and remaining half is to the left. So if I show this here, it is something like this. Right? Left face and the right face are equidistant from the surface charge. Let us say this distance is L, this is also L, and this area is A, right? Area is A. And by symmetry, we can say electric field on the curved surface will be parallel to the curved surface. So area, if I take any small area of the curved surface, this area will be perpendicular to the electric field. So flux through the curved surface is 0 because the electric field is perpendicular to the area. If I consider the right face, the area vector will be in the right direction. If I consider the left face, the area vector will be in the left direction. And electric field will be in the left direction for left face, and electric field will be in the right direction for the right face. So if I calculate the total flux, for the left face it will be EA, and for the right face again it is EA, right? So it comes out to be 2EA, and by Gauss's law, flux is through a closed surface is nothing but the charge enclosed divided by the epsilon naught. So charge enclosed will be the charge contained in this surface. So this surface has an area A and the surface charge density is sigma. So charge enclosed will be sigma times the area divided by epsilon naught. So from here electric field comes out to be sigma by 2 epsilon naught, and it will be normal to the surface, right? So next is the electric field between two infinite thin plane parallel sheets of uniform charge, surface charge density sigma and minus sigma is sigma by epsilon naught. Let us see. So here we have given two infinite sheets. One is having a surface charge plus sigma, other will be having surface charge density minus sigma. And we have just proved that the electric field by a infinite line charge is sigma by 2 epsilon naught. So if I consider a point between these two sheets, if this is 1 and this is 2, so the electric field by the first surface will be in the right direction, that will be E1, let us say. And the electric field by the second surface, since second surface has a negative charge, so it will be towards the negative charge. So this is E2. So E1 is having magnitude sigma by 2 epsilon naught, and similarly E2 is having the same magnitude sigma by 2 epsilon naught. So the net field at this point P will be sum of these two. So E1 plus E2, because both are pointing in the same direction. So this comes out to be sigma by 2 epsilon naught plus sigma by 2 epsilon naught becomes sigma by epsilon naught, right? Hence proved. Clear? Right. So now let me take one more case. If we have given a conductor, right? If there is a conductor, let us say there is a conducting sheet. So this is a conducting sheet, infinite conducting sheet, which is having surface charge sigma, right? And if I take so it's a conducting sheet. If I consider a Gaussian surface like this, now in this case, again, we can say the flux will be electric field is in this direction, area vector is in this direction. Similarly, electric field here will be in the left direction. Area vector is in the left direction. So it will be 2 times EA, and that will be, now we have two surfaces, right? Both area A and surface charge density sigma. So it will be 2 sigma A by epsilon naught. So here E comes out to be sigma by epsilon naught. So do remember this. If we have a conducting surface, then just outside the conducting surface, the field will be sigma by epsilon naught. Okay, now let us see some illustration. Consider two hollow concentric sphere S1 and S2 enclosing charges 2q and 4q respectively as shown in the figure. Find out the ratio of electric flux through them. Very easy. So in surface 1, how much charge we have? 2q. So we can say the flux through surface 1 will be 2q by epsilon naught. And if you look at the charge, how much charge is present inside surface 2? It will be 4q plus 2q, because 4q and 2q both are inside surface 2. So flux through surface 2 will be 6q by epsilon naught. So if you want to find the ratio, it will be 1:3, right? Now let us see the second question. How will the electric flux through the sphere S1 change if the medium of the dielectric constant epsilon r is introduced in the space inside S1 in place of air? Now, if we introduce the medium, then the epsilon value will change, permittivity will change, and the Gauss law will become E dot dA, it will become Q enclosed divided by epsilon r times epsilon naught. So now the flux linked with S1 will become 2q divided by epsilon r times epsilon naught. So that should be the answer of this question. Let us see another question. A small metal sphere carrying charge plus q is located at the center of a spherical cavity inside a large uncharged metallic spherical shell as shown in the figure. Use Gauss law to find the expression for electric field at points P1 and P2. Right, so we have given a conductor, a metallic sphere at the center. So this is the metallic sphere which is having a charge Q. And there is another metallic conducting shell which is having some thickness, and it is placed concentrically with this sphere, and it is uncharged, right? Uncharged. So what would happen? So due to this positive charge, what would happen? There will be some induced charge on the outer shell. So let us see. So we have to find the electric field at point P1, right? So but it is very easy to find the electric field at point P1. So we can draw a Gaussian surface like this. If the distance of point P1 is R, then we can say the charge enclosed by this Gaussian surface will be Q, and integral E dot dA can be written as, by symmetry we can say the electric field at P will be normal to the surface at every point, right? Every point on this surface, the electric field will be normal to this, right? So this can be written as E times integral dA. And by symmetry, we can say electric field will be having a constant magnitude at any point on this Gaussian surface. So this can be written as E times 4 pi R square, and the charge enclosed is Q. So Q divided by epsilon naught. So electric field will be Q upon 4 pi epsilon naught R square, right? So that is the electric field. Now, in order to find the field at P2, so we have to see like how the charge is being induced on the outer shell. So if I draw a Gaussian surface which is passing through P2, right? So we know that inside a conductor, the field is zero in electrostatics. So since P2 point lie inside the conductor, the field at P2 will be zero. So field at P2 is zero because it lies inside the conductor. And if I want to prove this by Gauss's law, so what I can say, since it is inside the conductor, field is zero, so there will be a negative charge which is induced on the inner surface of the shell. And this negative charge must be having a magnitude of Q. So it will be minus Q, right? So if you look at the net charge enclosed by this Gaussian surface, it will be zero. So the field will be zero. So that is the answer of this question, right? Now let us see one more question. So two concentric metallic spherical shells of radii r and 2r are given a charge q1 and q2. The surface charge density on the outer surfaces of the shell are equal. Determine the ratio q1 and q2. So we have given two concentric shells. So this is the first shell and this is the outer shell, right? And I'm showing some thickness in the outer shell. Right, so this is given to us and this radius is r and it is given as 2r. And we have given some charge q1 to the inner shell and q2 to the outer shell. And as we have seen in the last question, the inner surface of the outer shell will be having the opposite charge of q1, right? So if I look at the inner surface of the outer shell, this charge will be minus q1, right? Because if I consider a Gaussian surface which lies inside the material of the outer shell, the the electric field will be zero here, so flux should be zero. So to have flux to be zero, the net charge enclosed should be zero, right? So that's why there is minus q on the inner surface of the outer shell. If it is minus q1 on the inner surface of the outer shell, what should be the charge on the outer surface of the outer shell? It will be, since the charge on the outer shell is conserved, on the outer surface it will be q2 plus q1, so that the total charge on the outer shell remains the same. Now we have given the surface charge density on the outer surface of the shell are equal. Outer surfaces of the shells are equal. So it means surface charge density on the surface 1 will be q1 upon 4 pi r square, and surface charge density on the outer surface of the outer shell will be q1 plus q2 upon 4 pi 2r square. And we have given these two surface charge densities are equal. So sigma 1 is equal to sigma 2. So we can say q1 upon 4 pi r square is equals to q1 plus q2 upon 4 pi 4r square. So this 4 pi r square will get eliminated. So we have 4q1 is equals to q1 plus q2, or 3q1 is equals to q2, and q1 by q2 is equals to 1 by 3. So the answer is 1:3. So that is the answer. Now let us see one more case. A spherical conducting shell of inner radius r1 and the outer radius r2 has a charge q. A charge small q is placed at the center of the shell. So we have given a spherical conducting shell which has two surfaces. The inner surface has a radius r1 and the outer surface has a radius r2. And we have given some charge q. A charge small q is placed at the center. So we have placed a charge small q at the center. What is the surface charge density on the inner surface and the outer surface of the shell? So we know that on the inner surface the charge will be minus q, because by Gauss law the field inside the conductor is 0. So it has to be negative q. If it is negative q and the charge on the outer shell is conserved, on the outer surface the charge will be capital Q plus small q, right? So inner surface it will be minus q, and the outer surface it is capital Q plus small q. Write the expression for electric field at point x greater than r2. So if we have a point outside, if I consider a Gaussian surface, right? So this radius is r. So at this point, how much charge is enclosed? So q enclosed will be what? It will be q and small q. So q plus small q divided by epsilon naught. And what is the electric field? So by symmetry, we can say the electric field at this Gaussian surface will be normal to any small area element. So it is normal to that. So we can say integral E dot dA can be written as E times 4 pi r square. So E times 4 pi r square will be capital Q plus small q by epsilon naught. So electric field will be q plus small q upon 4 pi epsilon naught r square, right? And this, let us see one more question. Two infinitely large plane thin parallel sheets having the surface charge density sigma 1 and sigma 2 are shown in the figure, where sigma 1 is greater than sigma 2. Write the magnitude and the direction of the net field at the region marked 2 and 3. Okay, right. So between the plate, let us say at this particular point, the electric field by the first sheet will be in the right direction, and the electric field by the second sheet will be in the left direction. So this is E1, this has to be E2. Since sigma 1 is greater than sigma 2, E1 will be greater than E2. So field at 2 will be E1 minus E2. And we know that the electric field by an infinite sheet of charge is sigma by 2 epsilon naught. So this will become sigma 1 by 2 epsilon naught minus sigma 2 by 2 epsilon naught. So it will be sigma 1 minus sigma 2 divided by 2 epsilon naught. Now what is the electric field at region 3? So here the electric field by the first sheet will be in the right direction, E1, and by the second is also in the right direction. So here electric field at region 3 will be sum of the fields. So E1 plus E2. So this will be sigma 1 plus sigma 2 divided by 2 epsilon naught, right? So that is the answer of this question. Next, a uniformly charged conducting sphere of 2.5 as its diameter has a surface charge density of 100 microcoulomb per meter square. calculate the charge on the sphere. So we have given uniformly charged, right? So it's a insulator, you can say non-conducting sphere, which has uniform, no, sorry, it has a surface charge density, right? So it is not a non-conductor, it's a conducting sphere, right? It's a conducting, it is given, right? It is a conducting sphere. So the charge will be present only on the outer surface. And we have given surface charge density as 100 microcoulomb per meter square. And the radius will be 1.25 meter, half of the diameter. So charge will be sigma times the area, curved surface area. So that will be 100 microcoulomb times area will be 4 pi r square. So 1.25 square, right? So from here we can find the charge on the sphere. Total electric flux passing through the sphere. So how much electric flux is passing? So in that case, we can assume a Gaussian surface, right? So they are asking about the electric flux passing through this Gaussian surface. So that will be the total charge enclosed divided by the epsilon. So that should be the answer of this question. So we'll put the values, we'll calculate the answer up to the 2 decimal places and we'll get the answer. So like have you, so I have covered all important concepts and all different types of numericals that can be asked and even all derivations that can be asked from this chapter. So in the next video, I'm going to cover electric potential and capacitors. So stay tuned and do subscribe our channel for more such videos. Thank you.